Now uniform circular motion. When any object or the particle is moving on the circular path with constant speed, then the motion is called uniform circular motion. Then the motion is called uniform circular motion. Okay. Now, for this uniform circular motion of the particle, we have to derive the equation of acceleration. Okay. Now see, we already discussed this thing. When any particle is moving on the curved path, then the velocity at any point that is in tangential direction. Now here the speed is constant. It implies that the magnitude of velocity that remains the same one, but direction that will be continuously changing one. Suppose here we consider any particle which one is moving on the circular path having radius equal to r. Now at a particular instant t1, the position of the particle on the circumference of the circle, that is at P. And now here if we prepare the vector OP, and we can say that is the vector R1, and here we consider the origin of Cartesian coordinate system that is also at the center of the circle. Then we can say R1 is the position vector of the particle at time t1. Now the velocity, so velocity that is in tangential direction. So here we can represent the velocity vector v1 in the tangential direction, and this radial and this tangential direction are perpendicular to each other always. Now suppose after some time your particle reaches at position q. Suppose at position q it is at time t2. Now here if we prepare the vector OQ, then we can say the position vector R2 is the position of the particle at some time t2. Now at that time the velocity is v2. Now magnitude of v1 and v2, that is same one because it is moving with constant speed, but the direction is changed. Now what will be the acceleration? Okay. Now to find out the acceleration, let's think about the change in velocity. Now see here, when the particle moves from P to Q, then this arc PQ subtend an angle delta theta at the center. Okay. So here to understand the direction of change in velocity and direction of acceleration, represent these velocity vectors as shown here. So take the point O dash, and from there represent vector v1, as well as from the same point represent vector v2, in such a way that the head of v1 and v2 both lies, see this point head both lies on the x-axis. Like that, prepare these two vectors v1 and v2 here. So if we take p dash q dash vector, then that will give you delta v, the change in velocity. Now here we can easily understand the direction of delta v. See this direction. So if we think about the direction, that direction is towards the center of the circle. So here the triangle O dash P dash Q dash is prepared, and here the triangle form, that is OPQ. These two triangles will be similar triangle because this angle is delta theta, this angle is delta theta. And this side by this side, that is 1, because magnitude wise velocities are same one. Similarly, here the radius of the circle that remains the same one. So this side by this side is same one. So these two are similar triangles. Clear? Now, magnitude of R1, magnitude of R2, that is the radius of the circle R. Magnitude of V1, that is magnitude of V2, that is the speed of the particle V. Now, these two triangles are similar triangles, so we can write delta V by V, that is equal to delta R by R. So, delta V, that is equal to V by R, delta R. Now, acceleration that is delta V by delta T, but we want instantaneous. So we can write limit delta T tends to 0. This delta V by delta T, that we can write V by R, delta R by delta T. So we can rewrite this one like this, V by R, limit delta T tends to 0, delta R by delta T. But this limit delta T tends to 0, delta R by delta T, that can be written as dr by dt. But dr by dt, that is again V. So we can write A equal to V by R into V. So A, that is V square by R. And here in suffix we write C, because the acceleration that is always in the direction of delta V, and delta V is towards the center, therefore acceleration is also towards the center, and therefore this acceleration is called centripetal acceleration, or it is called radial acceleration. So this one is the acceleration of the particle which one is executing uniform circular motion. Clear to all of you? Now see, when your particle is moved from P to Q, it's obtain an angle delta theta. But now the linear distance covered, that is arc PQ, and it's obtain angle delta theta in time interval T2 minus T1. So here when particle is moved from P to Q, the distance traveled in time T1 to T2 is arc PQ. Okay. Now, during this distance covered, the angle subtended at the center of the circle, that is delta theta. And this delta theta is called angular displacement. Now, we discussed this thing, displacement upon time interval, that is speed or velocity we can say. Similarly, if we take angular displacement upon time interval, then it will give you angular speed. And angular speed is denoted by omega. This one is pronounced as omega. Angular displacement, that is delta theta upon time interval delta t. Unit becomes radian per second. Now we know this thing, angle that is arc upon radius. In second chapter we studied this thing. So angle that is delta theta, arc that is delta s upon radius r. Now, linear velocity v, that is limit delta t tends to 0, delta s by delta t, distance travel upon time interval. So we can write limit delta t tends to 0, and now delta s, that we can write from this one r delta theta. So delta theta into r, this delta t as it is. So we can write limit delta t tends to 0, delta theta by delta t. But here this delta theta by delta t with limit delta t tends to 0, if we take, then we can say that is omega. So V equal to omega into R. Now omega, that is 2 pi by t. અત્યારે તમારે આ યાદ રાખવું પડશે, ચેપ્ટર 7 ની અંદર આ આવશે, અથવા તો અત્યારે એવી રીતે તમે યાદ રાખો કે angular speed, that is angular displacement upon time interval. So as per that definition, if particle completes one revolution, then the total angular displacement, that will be 2 pi radian, and time taken to complete one revolution, that is called periodic time, and it is denoted by capital T. So by definition we can write angular displacement, that is 2 pi radian upon time t. So here V equal to 2 pi by t into R, that we can write. But 1 upon t, that is a frequency. So we can write 2 pi f also, omega equal to. Now we have centripetal acceleration, that is V square by R. Now first we substitute V equal to R omega. So R square omega square by R. So you will get R omega square. So centripetal acceleration, that you can write R. Now omega, if is replaced by 2 pi f, then you can write 4 pi square f square. Here be careful, I use the symbol small f for frequency, and see your text. In text, the symbol used, that is nu. That is nu.